produce coffee there. And this is the university installations, and back there is the coffee plantation. Here I showed where is the recording point and where we were supposed to record. Here is the campus of the university. Here in the left is how it looks. Coffee plantation is a bit different from the regular coffee monoculture, which is only coffee plants. Here we might have some shade, and it helps to have more diversity, since those trees are planted there to give some shade and to control the sun radiation and the temperature in some Colombia coffee fields. This is the coffee we produce at the university. One of the basic recording settings for the DR40 recording. Here, how the recording was made during the year 2015. What we made was taking one on each month, one day, 24 hours, were randomly choose to make the recording, and then the recording were divided into 20-second lapses, and then the first, the 10th, 20th, 13th, 4th lapses were taken for their analysis. What we try to make is make a kind of sample space to try to describe the power spectrums. Normally, what will happen in power spectrums is this kind of plot, and we have a lot of variations, and sometimes it's difficult to compare one power spectrum with another, because normally they are not the same. They might look similar, but not the same. And then what I made was to divide the power spectrum and to make some like kind of a code divided in several sections and bands that it looks here. Then the frequency was divided into 9 sections, and inside of each of those sections we divided in 3 bands. And the intensity inside those bands was divided in 7 intensity levels. So for each of the sections, we have 343 intensity and frequency combinations. It still looks well like a bit complex, but the idea was to have like a code to see if some of those combinations of intensity and frequency are repeated, happen several times, or just appear sometimes, to see how it changes over time. So what we saw in general is like the changes in the first 6 sections. As the frequency increases, we have less variations. There is like a graphical form to show those variations. And here maybe it's easier to understand. What I made here is that here are the 7 intensity levels, and here are the 9 sections. Then what we see is how here for each of the analyzed sections we have here the time, how it changes, and on which parts of the power spectrum don't change much along time, like in the higher frequency. If we go here down, the frequency increases here. Then here there are not much changes, but in the lower and middle frequencies we see more changes. What we wanted to see is how many of those possible combinations we create or we're going to appear along the year, and which of them appear more, which of them appear less, and which of them do not appear. And statistically, we made this model in which from all the 343 combinations we have, we expected to find just a few of them which are which define the soundscape. From this graphic, we see that if we would have more combinations, then the probability of the model to accurately describe the soundscape will be less. And if we find less combinations, then the model might describe accurately the soundscape, even there are few combinations. If we compare with the continuous power spectrum light. In the results, the first we saw is this kind of model where we in this first graph with this in February we have the distribution of the combinations. Then we have some of the combinations appear most of the time. For instance, this combination appears more than 50% of the time. The next one appears much less, 10%, and the other combinations appear much less. And when we start adding more time to the analysis, here only February, then February to March, to April to May, until February to December, the distribution of the relative frequency maintains the same shape and fits this model we have here. What we have from February to December, if we accumulate data, is that this A and B parameters are changing also according to a second model. What we see here is that the appearance of different combinations has some regularity, and some of the intensity frequency combinations related with power spectrum distributions has this regularity, and they don't randomly appear in the ecosystems. We understand that if some of these combinations appear, I mean, appear more most of the time, then maybe they are like the more successful intensity frequency combinations. Here is this model. This model explains how the variables A and B from the model we just showed, this A and B variables change according to the number of lapses are analyzed. So these variables are also changing gradually and can
You have 2 minutes left
into the model. Okay. And finally, what we found was the number of combinations also does not increase all the time. I mean, as this logarithmic function, and from this we can predict how many combinations might appear in the ecosystem if we continue doing sampling. This might reduce the time consumption and the effort to make sampling and find combination and find how many combinations are in the ecosystem. And finally, we have this graphic that shows which combinations appear all the time along the year, which are temporary, and which of them are sporadic, which can be useful also to compare the combinations that appear from one year to another or when we need to make comparisons in a soundscape which is being affected by some negative impact. Okay, thank you.
I see you have another slide. You have just a bit of time, if you like.
As a conclusions, we can say that the soundscape and the shady copy plantation show the accumulated relative frequency fits the model very well, which are 2 of 0.94 on average. And according to its appearance, it is proposed that there are base, temporary, and sporadic combinations in a soundscape, and the predominance of frequency density combinations could be understood as an adaptation of acoustic community to the most successful forms to show the sound spectrum.
Okay, now there's time for questions. Klaus Riedi, please go on with your question.
Yeah, thank you for this interesting talk. I think it's very important to have these data from shallow coffee plantations. Do you think there's any chance to get information about the combination you mentioned with real species in the field? So at least some of the prominent combinations which are occurring all the time should be correlated with a certain species, which could be something like an umbrella species or an indicator species. Do you think that's possible?
Not always. In some cases, we did relate these combinations with some events at the soundscape, but not particularly with the species, because the resolution is not that high.
Mm-hmm. Thank you.
Thank you.
Other questions? No one is willing to ask something? So I have a small comment, a little comment to do on this work, because it relates with an agro ecosystem. And now we are facing with very big problems with climate changes, environmental changes due to human activities, agriculture, and so on. And I think that is interesting to analyze solutions, agro-ecosystem solutions, able to mix natural features with natural ecosystem services with the productivity we need. So I think it would be very interesting to expand your analysis to different types of coffee plantation, traditional and more intensive and more extensive coffee plantation, and also to understand how natural soundscape can mix with agro-ecosystem soundscapes. So I think it's really interesting to work on the transitions from agro-ecosystems to natural habitats also. Other questions? No more questions, so I can introduce the next